All right, ladies and gentlemen, happy spring break is over. Are you? Did it feel like spring break? Well, it's Monday morning. It's about 8:30 right now for me. I don't know what time you guys are getting up or what time you guys are getting to this, but I hope everybody's doing okay. Please remember these your physics projects are due Wednesday. If you need a bit more time, please let me know. I think about half of you have already handed them in. But please do let me know if there's issues or questions or problems. Don't struggle alone in silence with this stuff. We're jumping right back in. There's no real direction from the education department yet to say how things are changing. So everybody's still expected to work. Teachers expect to teach, students expected to learn. So if there's something stopping you from that you don't have a whole lot of control over, please let me know. All right, so I photocopied the rest of the physics. It's a lot. Oh, guess what? These are double-sided. Some are just notes, and some, I'll be honest with you, we're just not going to get to. That's the year it is. I couldn't figure out how to get rid of the black when I photocopied this, so again, please don't tell Mr. Taves. It is what it is. It's actually worse with the pre-cal stuff. All right, that scratching you hear is cat in the litter box. Okay, work, energy, power, and society. This is where you pause it and you draw all the details of the parrot. Make sure you get all these little... I hope you know I'm joking. Don't do that. If your parents are listening, let them know. That's not how we roll. Anyway, work, energy, power, and society. That's the name of this unit. Okay. First lesson, mechanical work. I'll let you take that down. Hey, you paused it and unpaused it. Good job. Okay, mechanical work. Work, the simplest terms, work is force times distance. Okay. Delta D is the change in distance, and there's also, we're going to make it a little bit more interesting when we do F equals cos of D. It's not that crazy, don't worry. Anyways, work is force times distance. When the force applied displaces an object in the same direction as the applied force. That's really important. You got to underline that. When the force applied, don't cross it out. Same direction as the applied force. If I'm pushing on this table, there, you can tell that I moved that, right? It's in the same direction. So work is being done. Oh, I can pull it far enough to get rid of that shadow. Work is being done. Same direction. It's not a vector. It's a vector times a vector, yes, but the final answer is not a vector. You'll find out soon that work equals energy. Energy is also not a vector. It's in joules. A joule is a Newton meter. Some of you, I have a feeling Calvin, you'll be like, I'm just going to put Newton meters. You can, but it's joules. Time, velocity, and acceleration don't matter in this equation, but they may be needed to solve for these two. Hey, look. Might as well put these bad boys in, hey? So those are all vectors. All right, I want to ask if there's any questions. I'll never know. My page is done. Get out of here, parrot. All right, so it's also represented by work equals force cos of theta times d. So when the force applied, oh, sorry, I got to let you take this down first. Let's take it down and process it. I'll stop for a second. Okay, you took it down. Good. It's represented by W equals F cos theta delta D. When force applied displaces an object in a different direction from the applied force. So when it says different, it doesn't necessarily mean like the polar opposite. Just here's a good example. This suitcase is being pulled in this direction. Displacement, it's not the best photocopy. It's being pulled in this direction. This came right out of your textbook, by the way. It's pulled in this direction, but the actual force is this way. Well, as we know, because of our component vectors and all the work that we've done on that, with this vector, there is a horizontal component and a vertical component. The vertical component to us is useless unless this thing is going vertically. So it doesn't matter how much you pull up. There's no work done unless this thing moves that way. So the horizontal component is what we're interested in. That's the part that's pulling, and that's the direction the suitcase is going. We'll get into negative work in a second. But cos of theta, so think of, all of you except Calvin, although you've done it, think of trig. This is theta. If we say cos of 1, or sorry, cos of 0, so let's say there's no angle here. That's just horizontal, right? Cos of 0 equals 1, if you think of your unit circle. Cos of 90 degrees, straight up, is 0. So if he's pulling straight up and the thing's moving this way, it's 0 work. All right, we're going to do lots of examples in case that's a little heady for you. Notice the vertical work down is 0 because there's no displacement in the direction of the vertical force. Cool, cool, cool. Negative work. Give you a moment to take this down. Negative work. Kinetic friction results in negative work because the displacement is in the opposite direction. Okay, so if you have a car rolling down a slight incline toward you, and you're trying to stop it, and you're pushing, you put your hands on the car, and you're trying to stop it, but you're moving backwards. You're pushing away from you, but you're moving backwards. You're doing negative work because the force you're applying is going one direction, the motion the other. Now, eventually you'll stop that car, and then maybe you'll push it the other way, then it becomes positive work. Cool, cool, cool. Graphing in a force displacement graph with displacement on the x-axis, we can find work by calculating the area covered. See figures 7 and 8. No, natural question, and quite often I would say, whether or not you'll be tested on this, whether or not you kind of need to quote unquote know it. This is probably going to be up to you because you're probably going to be creating your own test at the end of this unit. Because we're not coming back at least before the end of this month. So anyways, a graph can also be used to calculate work done when the force is not constant. See figure 9 on page 227. When I say not constant, basically what it's saying is it isn't just neat little boxes on the graph. Anyway, you have a look at that and don't stress about it either. I would not ask questions about this. Not important to me. Done with that sheet. Oh, look, page 229, 1 to 11. What it doesn't have, I didn't change anything on these before I printed them out. I was just trying to be in and out of the school really quick. My home printer doesn't have ink. We're doing lots of tutorials. You want me to write them here so you know exactly what they are? If you want to hear, so there's practice 1, which is page 223. Practice 2, page 225. Practice 3, page 226. And 4, page 227. You dig? Let's get to those practices, shall we? I want to keep this together. That's important. And now let's switch it with scrap paper. Okay, probably make this brant. I just realized I didn't even check to see if that it's focused, man. I hope it was. I think it was. I was looking at the screen. All right. Practice 1, as we all remember, page 2. It actually starts, like the tutorial starts on page 222, but the practice questions are page 223. As I've said in years past, meaning last time I saw you, it's always good to read the textbook. It's always good to read the unit that we're on. It's always good to read the tutorials. You are kind of responsible for that. So if you're like, well, I didn't understand this, didn't understand that, did you look at the tutorial? Did you read through it? No, then that's where you got to go. All right, practice 1, page 223. Numero uno with a bunch of parts. A 0.5 kilogram mass equals 0.5. I hope that's clear. That looks clear to me. I'm just going to double check. clearer. That actually looks worse. Oh, it's got some arms in it. Holy, this thing's confused. I'll put this in. There we go. Mass equals 0.5. VI is 3. You might be thinking, I'm not even reading this, I'm just pulling information out. I will in a second. And you might be thinking, this is way too crazy to start. Why do we got all this information? Hang on, brothers and sisters. Well, acceleration is 1.2. Clearly that says 1.2. The time is 2. Okay, I'm going to read this. A 0.5 kilogram lab dynamics cart with an initial velocity of 3 accelerates for 2 seconds. There's the time. Time for 2 seconds. 1.2 meters per second squared right when pulled by a string. Okay, first thing I want to see are velocity, acceleration, same direction, or one of these going to be negative. Velocity is right, acceleration is right. Okay, we're cool in the gang. There's no friction along the cart. Beautiful. A. Calculate the force exerted by the string on the cart. Force equals mass times acceleration. Mass is 0.5. Acceleration is 1.2. Goodness, we don't even need a calculator for this one. 0.60 newtons. And then it'll be to the right. Cool, cool, cool. This is F equals ma. B. Calculate the displacement of the cart. Okay, it wants the displacement because work equals force times displacement. We don't have displacement here, so we got to use the formulas. So we're going to find the formula that does not use final velocity because we're not given it. We don't need it. It's the third formula. So D equals VIT. D equals VIT plus 1/2 AT squared plus 1/2 AT squared. Okay, displacement equals initial velocity is 3, time is 2, plus 1/2 acceleration is 1.2, t squared, t is 2, 2 squared is 4. So we need a calculator for this. 3 times 2 is 6. 1/2 of 4 is 2. 2 times 1.2 is 2.4. So that equals 8.4. And if we're doing 2 sig figs, then we're done. 8.4 meters. Right. Turn the page, see if I'm right. Holy moly, 2 in a row. C. What does C want? Probably the work. Calculate the mechanical work done by the string on the cart. Okay, so we have our D. We have our F. F times D equals work. Force is 0.6. Displacement is 8.4. 6 times 8 is 48, so that's 0.48. 0.48, 0.504, I think. 0.504. 0.6 times, what the? Let's wait till this is done drawing. Kids' calculator sitting here, so I thought I'd use it. 0.6 times 8.4 equals 5.04. So 5.0 joules, no direction. This is not a vector. So some of you are like, I don't write that stuff anyway. You should for the other ones, Richie. 5 joules, 5.0 joules, okay? That's practice 1. 1 done, 3 more to go. Practice number 2, page 225. Numero uno says, a person cutting a lawn, a flat lawn, oh, that's good, pushes a lawnmower with a force of 125 newtons, so F equals 125, at an angle of 40 degrees below the horizontal. Theta equals 40 degrees below the horizontal. We'll talk about that in a second. For 12 meters. D equals 12. Okay, so if we're pushing a lawnmower, whoa, this is a space age lawnmower. Okay, so now it says, so they're going this way, because they're pushing it, 40 degrees below the horizontal. So this is where the 40-degree angle is, which also means that the 40-degree angle is here, and so it works for us. Just make sure that it's giving you the right angle, because it might be giving you an angle such that if it says 40, it means 50, because those two are supplementary. So just make sure you understand the angle that it's coming at. So all this is, my friends, work equals F cos theta D. Force is 125 cos of theta, so it's cos of 40 times 12. What I do, I always do this part first. Figure out cos of 40, depending on your calculator, how it wants you to enter it. Cos of 40, whatever it is, times 125, then times 12. It doesn't matter the order. It just matters on how your calculator operates. Cos of 40 is 0.766 times 125 equals this, times 12. 1149. When I say it doesn't matter the order, think of it like 3 times 5 times 7. 21, 105. That equals 105. It doesn't matter if I did 3 times 5, 15 times 7, or if I did 5 times 7 and then times 3, or 3 times 7 and then times 5. It's all going to equal the same thing if it's all multiplication. Here it's all multiplication. But plus or minus something in here, that changes things. So 1149. What are our sig figs in this thing? Is it 2, 3, oh, 3 sig figs. So it's 115 joules. Oh, 115 point, not 0.0, 1150. Goodness gracious. It is Monday after spring break. 1150 joules. Well, the answer gives it in kilojoules. Okay, 1, 2, 3, which is the same thing as 1.15 kilojoules. Both have 3 sig figs. This is a little less writing, but maybe not, because instead of that 0, you're writing the K and the decimal. It's up to you. I don't care. If this had like 16 zeros behind it, then yeah, go this route. Number 2. I'm going to need a drink of water. The father pulls a child on a toboggan along a flat surface with a rope angled at 35 degrees above the horizontal. Okay, so this is the toboggan, this is the kid. 35 degrees, this works. Okay, so theta equals 35 degrees. I keep telling you guys this as if like, well, this is all it has been. Just watch. Just be careful. Anytime you see degrees, make sure it's giving you what you need, because this physics textbook doesn't always. It likes to make you work. Theta equals 35 degrees. The total mechanical work done by the father over horizontal displacement of 50 meters is 2410. Determine the work done on the toboggan by the normal force. What? Determine the work? I thought I was going to ask for the force here. A father pulls a child in a toboggan along a flat surface with a rope angled 35 degrees above the horizontal. The total mechanical work done by the father over a horizontal displacement of 50 meters is 2410. Determine the work done on the toboggan by the normal force and the force of gravity, and explain your reasoning. Okay. Minor trick question. It's not asking for force. It's easy to figure out force, solve for F in this, but that's not what it's asking. It says there's normal force and there's gravitational force. How much work is being done by those? 0. If we're doing sig figs, 0.00 newtons. This is work of gravity. And the work of normal force, it's 0 because there's no displacement. This kid isn't suddenly floating because of the normal force or suddenly sinking into the ground because of gravity. No work is being done. Gravity is exerting a force. Normal force is exerting a force, but there's 0 displacement. Cool. Which basically works out the work equals, and then, I don't know, say the kid is 10 kilograms. 10 times 9.8 is 98. So the force is 98, but the displacement is 0. So 98 times 0 is 0. Cool, cool, cool. Can I write on the side? Will that be distracting? It looks like it will be. All right. Ooh, what is this? I got attendance reports. I don't know if I should use this. Well, I'll just hide that part. All right. Let's make a clear line here. Don't go below that. What are we on? Number 3. I'm going to pause this and get something to drink. Thursday. All right. Welcome back. That was instantaneous for you. Practice 3. Page 226. See, I haven't forgotten my French, even though we had spring break. Page, do you really say it that way? There is no work done for each of the following examples. Explain why. Okay. So in the first situation, you've got a student leans against a brick wall of a large building. I like that it says it's a large building, because if it's a small building, that student's going to knock that stuff over. So they're pushing with their super long arms on a really low spot on the wall. But the wall is pushing back. The wall's not moving. That's why there's zero work done. It's not zero force. Zero net force. But zero work. No, the easy answer here is displacement equals 0. It's probably going to be for all of these. Let's see. Part B. A space probe coasts at constant velocity toward a planet. Okay, so you've got this space probe. I have no idea what a space probe looks like, so I don't know how to draw it. So I'm going to draw... I don't know what that is. An earring? A ring? Someone lost a ring. And it's floating through space. Okay, now... the important part about this is it says that constant velocity. Constant velocity means acceleration equals what? 0. Force equals mass times acceleration. In this case, mass times 0. If force is 0, then work is going to be 0. Okay? 0 acceleration. Cool, cool, cool. C, last example, a textbook is sitting on a shelf. It's not where a textbook should be. It should be in your hands. So it's just here with all its friends. Just sitting there. It's not moving. It's not going anywhere. Gravity's pulling down. Normal force is pushing up. 0 displacement. Therefore, 0 work. These two, the displacement is 0. This one, the force is 0. All right? All right. Moving right along. Last example. Number 4. Where are we? Excuse me. Number 4, practice 4, page 227, numero uno. You even got my Spanish. Is uno? Is that a Spanish word? I think so. Ocho is. Curtis pushes a bowl of cereal along a level counter a distance of 1.3 meters. So displacement is 1.3. What is the network done on the bowl? Network. Oh, what's this mean? Friction, probably. What is the network done on the bowl? If Curtis pushes the bowl with a force of 4.5 newtons, so the applied force is 4.5, and the force of friction on the bowl is 2.8. Force of friction equals 2.8. We just need to subtract these two to get the net force. Does that make sense? It's kind of like if you're pushing with 4.5 one direction and your mortal enemy is pushing against you with 2.8, you're going to win. We just need to figure out by how much. So net force is 2.5. No, it isn't. 4.5 minus 2.8. What's that, 1.7? I have trouble with those kinds of numbers in my head. 4.5 minus 2.8. 1.7. Not a lot of trouble. So the net force, 1.7, is this to the right? Doesn't really matter, but I just want to know. Doesn't even say. So the net force is 1.7 for Curtis. The displacement is 1.3. Work equals FD, 1.7 times 1.3 is 2.21. How many sig figs in this bad boy? Just 2, hey? So equals 2.2 joules. You dig? That's question number 1. And last one. Number 2, a crane lifts a 450 kilogram beam. Okay, so mass is 450. 12 meters up, so it lifts it up 12 meters. Constant velocity, acceleration equals 0. This is net acceleration, okay, because it's lifting up. So we know gravity is involved somehow. Anytime anything's being lifted, gravity is going to be involved. Calculate the mechanical work done by the crane. Okay. If the acceleration is 0, that means it has to counterbalance acceleration due to gravity. So it is going up. The acceleration up, independent of gravity, is 9.8. Net would be 0 because 9.8 up cancels 9.8 down. You feel me? F equals ma. In this case, the mass is 450. Acceleration is 9.8. I keep hitting the graph button. 450 times 9.8, 4410. And then displacement is 12. Work equals force times displacement. 4410 times 12 equals 52920. 52920. How many sig figs? Just 2? Yeah, so that equals 53,000 joules or 53 kilojoules. That's it. It's half an hour of me talking without giving breaks to write stuff down or anything. What is the assignment? I don't remember. 1 to 11. 1 to 11 doesn't sound too bad. And then you see this. This is 1 to 11. So what I'm going to do is I'm going to give you guys today and tomorrow. So I'll still be checking in. I'll still kind of go over questions as you want. But I'm going to give you class time tomorrow. You dig? Hope you guys are doing okay. Talk soon.